A very good chance to get a review on this topic. Yeah, please.
Okay, so first of all, let me thank the organizer for inviting me to give this lecture. I'm really thankful for them. And it is not a good idea. So I have learned one thing. If I come to Korea, I'll force the organizer to have my talks at the beginning, because the Korean hospitality is taking a toll on me. So I should thank you for excellent arrangements.
Because I'm less jet lagged now than I was on that.
Okay. You are not going to dinners. Okay. So let me first introduce myself. So this is Indian map, and this is the state of Gujarat, which is in the western side of the country. And this Indian Institute of Technology is basically a group of institutes, in almost one in every state. So you can think of around 24, 25 such institutes are there. So they started with a technology in mind, but slowly the name remained, but they have evolved and become like universities. And this is the main building of my institute, which is in Gandhinagar, Gujarat, which is in that part of the country. So let me start this talk with the first. Like any black hole thermodynamics talk, this would be the first slide, which is the idea of black hole entropy. I mean, first few slides will be very introductory. Slowly I'll introduce more technical stuff. So we all know that there is this great idea by Wittgenstein in 70s. While discussing Wheeler, he proposed that if you throw a hot coffee cup into the black hole, basically a state with very high entropy, what happens to the entropy? And it turns out if the entropy is lost to the outer world, it seems there is an apparent loss of entropy, decrease of entropy in the outside world. And to save this second law, Wittgenstein proposed that black hole must have entropy, and he gave very interesting order of magnitude estimate of the entropy and come up with the condition that the entropy must be proportional to the area of the black hole. So this is well-known history. But important part is that this argument does not fix, or it cannot determine the proportionality constant. So this is the beginning of the black hole thermodynamics in 1970s. Of course, this is good news in general relativity, because in general relativity we have an exact theorem which we call the area theorem because of Hawking. What area theorem tells us? The area of black hole event horizon cannot decrease as long as certain conditions. I will discuss everything in detail. If you put certain conditions on matter and some form of cosmic censorship is valid, of course this has to be technically explained, then it is guaranteed that the black hole area cannot decrease by any process. Whatever you throw, whatever two black holes collide, the amount of gravitational radiation comes out must ensure that the area of the final black hole is greater than the sum of the area of the initial black holes. And this area theorem is very good news, because if indeed there is some relationship between area and entropy, then this is like a second law. So area theorem ensures that when a high entropic object falls into the black hole, the outside world loses entropy, but black hole area increases to compensate that loss. That's the idea. Okay. Well, if black holes have entropy, then they should have temperature. So that's the great breakthrough by Stephen Hawking, who proved, working on, in fact, he wanted to prove Wittgenstein wrong. If you look at the history, he didn't like the idea that black holes have entropy. But anyway, history worked in a different way. It is Hawking who proved, by using the quantum field theory in curved spacetime, that there indeed exists a temperature for black holes. But unlike the classical black hole, the black hole temperature is quantum mechanical. There is a H bar sitting there, which leads to the quantum mechanical temperature of the black hole. And the derivation of the Hawking temperature lies in a very deep mathematical structure of quantum field theory. The question is that what is the right choice of vacuum in a curved spacetime near the black hole? And if you want a vacuum which is well behaved, you can show that there in that vacuum there will be a Hawking flux. And if you are interested, you can look at this famous theorem in quantum field theory in curved spacetime, which ensures that as long as you choose the right choice of vacuum, the Hawking radiation is an inevitable fact. And the Hawking result, once you know the exact expression of entropy, you can go back and use the Clausius relation to fix the proportionality constant between entropy and area. This is the famous proportionality constant if you 1/4. And it is expected that any quantum gravity theory, at least in the leading order, should reproduce this formula. And this is one of the most beautiful formula we know in physics. It contains all the fundamental constants in nature. I mean, one could say that what we are looking at is a leading order result of any quantum theory of gravity. Of course, we don't understand this result completely. It immediately hints that there will be some microscopic structure behind the black hole, and there will be some counting of states. Of course, the string theory indeed, at least for certain class of black hole, not exactly for Schwarzschild black hole, shows that there are objects in string theory which accurately produces Bekenstein entropy for certain particular calculations. And this is the famous paper by Strobingen and Vafa, which gave for certain class of black hole a microscopic description of this formula. Very good. So what is black hole thermodynamics? So this is basically the main story, I mean summarized in 2 slides. So thermodynamics of black hole is basically the idea that there exists an intriguing analogy between the laws of black hole mechanics and laws of thermodynamics. At the classical level, this is just an analogy. But once you take Hawking's formula seriously, then it's the exact correspondence. The black holes indeed in our universe behaves like a ordinary thermodynamic object, and their entropy at least presumably have a statistical mechanical origin. So this is black hole thermodynamics summarized in this correspondence, that a thermodynamic system in equilibrium with temperature and entropy is think of to be equivalent to a stationary black hole. One stationary black hole is important. So the equilibrium state, the concept of equilibrium state in thermodynamics is parallel to the stationary black holes in general relativity. With, of course, there are other technical assumptions which I have to clarify, with Hawking temperature and Bekenstein entropy. And this correspondence is built on these following laws, and these laws called the first law, zeroth law, first law, second law. I have deliberately avoided to write the third law. There is a kind of third law in thermodynamics also, but even in ordinary thermodynamics, the issue of third law is not very clear. I mean, I can discuss at the end, so I'll stop till the second law. So the first zeroth law basically says the surface gravity is constant on a stationary event horizon. The first law ensures that there exists a Clausius relationship. You can think of this as surface gravity. So this is the Hawking temperature, T ds equal to dq. So all these terms needs to be defined. What do you mean by this d? What do you mean by this q? So I'll try to do that. And the second law is the famous area theorem, which ensures that the area of the black hole cannot decrease as long as you throw matter with positive energy. I mean, null energy condition is satisfied. And therefore, there exists an equivalence between the temperature of the black hole and the surface gravity of the black hole, entropy with the area. This is the story in GR. Of course, as I told you before, this does not fix the proportionality, because you can always put an eta here and eta here, which cancels out. So just by this relationship, you cannot say what is the absolute value of entropy and what is the absolute value of temperature. You need at least an independent calculation of the temperature or the entropy maybe. So this independent calculation indeed is provided by the Hawking, and once you know that this is exactly the temperature, then you know this is exactly the entropy. That's the idea. So this entire
Q is same as M.
What?
What is the relation between M and?
So I will come back to it. So there are different versions of black hole laws. So in the stationary comparison law, which is Wald and collaborators have given, then this dq will be identified as the change of the ADM mass dm. But there are more local versions which I will mostly discuss. In that case, these will be the energy with respect to the background killing field. I will describe more detail what is this actually. What is? I can't hear you. So that's what I am saying. So this eta, right? So this equation does not uniquely fix the, so you can always put a fudge factors. Unless you know independently what is temperature, you cannot fix what is the area. Okay. So in this talk, at least these 2 talks, I will try to show how to derive this law. Particularly emphasis will be zeroth law, first law. Of course, I will discuss second law, not in more detail, but in a reasonable detail. And the emphasis will be how to extend these laws beyond general relativity modified gravity theory, most importantly, trying to address how to generalize this law when Einstein's equations are no longer true. Okay. And what are the crucial assumptions and the open problems still remains in this classical derivation of these laws. So that will be the more or less the aim of this talk. So let's go ahead. Okay, so these are the classic references. So there is this famous review by Robert Wald, and that more or less summarizes the status of the field till 99. After that, there are some interesting development related to holographic entanglement entropy. There is this famous lecture by Townsend, which is classic, and if any students are there, I strongly suggest to look at this lecture. Then of course Ted Jacobson has this introductory lectures on black hole thermodynamics. This is very good if you want to really understand things like Hawking process, Trans-Planckian questions. This is very good lecture notes. Then Aaron has recently written a review which is called a survey of black hole thermodynamics. This is an excellent review. You want to understand topics related to generalized second law, which I will not discuss much here because of its technicalities. And also if you are interested things like holographic entanglement entropy and its relation to black hole mechanics, this is an excellent review. This is my review. So this has appeared in archive in last year. So whatever I'm going to discuss, the detailed calculations will be there in the review. So I will ask you, if you are interested in legal, you may want to look at this review. So there is this interesting book by Eric Poisson, which is, it's really a relativist toolkit. So the last few chapters indeed discusses the derivation of black hole thermodynamics, black hole's laws, and the derivation are quite detailed and quite interesting. And sometimes he also gives very interesting examples. So this is also a good book to look at. Of course, the classic book by Wald, there is no alternative to that book. That book is always there. And we also know the book by Hawking and Ellis, which is a bit technical, but sometimes if particularly related to second law, if you really want to know what is going on, you have to go and refer to that book. Okay, with this, let's go ahead to the technical part of the talk. So we'll start with Einstein's equation. Of course, on this audience, I don't have to explain what are these. So suppose I have a simple spherically symmetric solution. So I want to determine the spherical gravitational field outside a spherical star. In that case, I get the Schwarzschild solution. Of course, if it is a black hole, then the star has collapsed, crossed its Schwarzschild radius and become a black hole. In that case, I know that light cone behaves funnily in some coordinate system, and R equal to 2m surface looks like a null surface. And the idea is that the matter affects the causal structure and therefore the behavior of light cone. As a result, the R equal to 2m surface blocks any information going from inside to outside. So you can only go inside, you cannot come outside. Okay. So that's the idea behind calling R equal to 2m surface as the event horizon. Note that the Schwarzschild spacetime also has a time-like killing vector. In usual coordinate, it will have component 1, 0, 0, 0. That time-like killing vector has this following norms, and exactly if you at R equal to 2 gm or when g equal to 1 2m, the norm of this killing vector is 0. Okay. So this time-like killing vector becomes null at the, if you look from outside, if you go from on the horizon, in that limit, the time-like killing vector becomes null. So R equal to 2m surface has one property, that it is a causal boundary between inside and outside. And the second property, that there exists a time-like killing vector outside, which becomes null on the R equal to 2m surface. And therefore, on this surface, you can do a simple calculation. Just calculate this object by using the Schwarzschild metric. You can show that this kappa is just 1 by 4 gm. And this quantity is called the surface gravity. And it has an interpretation, at least for static case. It is something like there is an observer at infinity who is trying to put a unit mass static at the horizon. So the force required to do that, or the acceleration required to do that, will be measured by the surface gravity. So you can think of this as a acceleration at the horizon with respect to an observer at infinity, because the local acceleration at the horizon will diverge obviously, because it's a null surface, but you can measure with respect to an infinite observer. In that case, this will be the surface gravity. So R equal to 2 gm surface has the following property. It's an event horizon. It's also a killing horizon. By killing horizon, I mean there exists a time-like killing vector in the space-time, which becomes null on this horizon. And this is for a particular solution but it is possible to generalize these concepts without any use of any specific solution. That's the idea and beauty of it. That in Schwarzschild case, I can see as an explicit example this happening, but one can make it more general without any referring any particular solution. So that's the idea. How do you define an event horizon? Of course, for simplicity, let me assume an asymptotically flat spacetime. You can do it better. You can of course define event horizon in de Sitter space, but for the simplicity, it is easier to see for asymptotic flat states. And again, I will try to avoid more mathematically oriented words. When I say asymptotically flat, I simply mean the asymptotic structure is given by that of the Minkowski space. That means I can define a Scri plus and a space like infinity and Scri minus. That's all. Okay. And then a space-time has a black hole region if there are outgoing null geodesic which can never reach its future null infinity. So in Minkowski space, every outgoing null geodesic will eventually reach the special null infinity. Okay. So if you look at the past of the future null infinity, that is the entire space-time. Okay. But if you have a solution, if you have a situation that there are outgoing null geodesics which does not need to reach the future null infinity, then I will say there exists a black hole in the solution. So if you take this future null infinity and construct its past, which is this J minus of I plus, and as a set you subtract it from the entire manifold. Of course, this has to be very carefully understood. There is a closure involved here. I am just avoiding those issues of the limit points and everything. But intuitively, this idea is that if there are regions from which lights cannot go to the infinity, in that case such a region will be called a black hole. And the boundary of such a region will be called an event horizon. The good thing of this definition is that this does not require a specific solution. But the bad thing is that you have lost all physical meaning of it's very difficult to understand. For example, if I ask you, can you prove that this event horizon is a null surface? That's not easy. Okay. So, in fact, you should look at this proof in Penrose. It is there discussed also in Hawking and Ellis' book. It takes several steps to prove the event horizon defined in this way is also always a null surface generated by the null geodesic, which is future complete. What it means is that there is no caustic in the future, all the caustic is in the past. So things once entered into the event horizon cannot come out. Okay. So defined in this way, I have not referred to any particular solution. So whether the solution could be time dependent, I mean there may be a rotating black hole, radiating gravitational energy, whatever. The hope is that if this definition must hold true, so there may be event horizon even a highly time dependent situation. Okay. But there is another concept which is called a killing horizon. What is a killing horizon? If your space-time is stationary, that means you have been given a space-time which has a time-like killing vector. This is given to you. In that case, if there exists a hypersurface for which the killing vector becomes null, then it is called a killing horizon. Very simple. You are given a killing vector, calculated norms, look at everywhere if there is any surface on which the killing vector has a zero norm. Everywhere on the surface, not on a particular point. Okay. In that case, you will call this surface to be a killing horizon. Well, look at the event horizon is defined in far more generality. But killing horizon is only defined for stationary black hole, stationary system. And there may not be any relationship between killing horizon and the event horizon. And two examples I will give. Consider the flat space. Everybody will agree in flat space there is no event horizon. Every light ray eventually will reach to the future null infinity. Every inertial observer will get information as long, if he waits for infinite long, he will get information from everywhere. So there is no event horizon in flat space. Okay, I mean there is little trick. What you think of flat space today, tomorrow you may be already inside the event horizon. But I am talking about an eternal flat space. In that flat space, you can construct these Rindler patches, and here is an uniformly accelerated Rindler observer, which is the integral curve of the boost killing vector. So flat space has 10 killing vectors. One of them is this boost. This is a boost killing vector, and you can construct the norm of the boost killing vector. Okay. So these are the integral curves of the boost killing vector, and if you calculate this norm on the light cone, of course this norm vanishes. That means this x equal to plus minus t surface is a Killing horizon with respect to the boost Killing vector this. Okay. But this is not an event horizon. So Killing horizon may or may not have any relationship with the event horizon. Let's look at the reverse example. An event horizon which is not a Killing horizon, that is easy to define. This is the Vaidya spacetime. It's an ingoing Vaidya spacetime. So what is this spacetime? It basically tells you that you have an ingoing spherically symmetric radiation field. Okay. It's kind of a accreting, spherically symmetric accretion onto a star. Okay. And you write down the exact solution outside. And you know this is the Vaidya solution, where this is the time dependent mass. Okay. And this V's are the time coordinate t plus r. And this Vaidya black hole is basically a black hole which is accreting matter. It has no time like Killing field. It's a dynamical spacetime. In that case, of course, there is no Killing horizon. But you can immediately look at the equation of the null geodesic and with appropriate boundary condition and write down an equation for event horizon. So Vaidya spacetime has no Killing horizon, but it has an event horizon. Okay, you may think of a spacetime which accretes matter and ultimately reach to a final black hole of mass capital M. So the final event horizon is 2m. This is the first order differential equation. You give the boundary condition that final event horizon has to be 2m. So you can solve it uniquely. It's a surface r as a function of v. The area of if it is ingoing matter, the area of the event horizon will increase and ultimately become some final event horizon. So here is a Killing horizon which is not an event horizon. This is an event horizon which is not a Killing horizon. So the question I need to answer that, then what is the relationship between Killing horizon and event horizon? Well, it's a famous theorem. This is called a strong rigidity theorems, because there are several such theorems. It is proven by Hawking for the 4-dimensional case and then extended by Wald and his collaborator, Wald and Holland, for the higher dimensional case. The theorem is tricky, highly technical its proof, but I'll give you the main meaning of the theorem. The theorem says that in a stationary spacetime, suppose you have an event horizon with a spacetime which has a time-like Killing vector, then it is guaranteed, modulo certain technical condition and energy condition holds true, it is guaranteed that event horizon must be a Killing horizon. So remember that r equal to 2m surface, that's the event horizon, that's a static spacetime, so therefore it has a Killing vector, time-like Killing vector, and you also found that it is a Killing horizon. Similarly for Kerr is a stationary spacetime. There exist two time-like Killing vector, the time as a Killing vector and also the t the another Killing vector. Okay, and you can also show that the Kerr Killing vector is all Kerr black hole horizon, black hole not the ergosphere. The horizon is also a Killing horizon, but the Killing vector is not the time, but the another Killing vector. So the relationship between Killing horizon and event horizon is that in stationary spacetime, every event horizon must be a Killing horizon. Must be. Of course, modulo certain technical condition holds true, which it's not important to, they're important, but it will be boring if I mention it. So Kerr, for example, even for Kerr black hole, this Killing vector is not exactly the time 1 0 0. It's a 1 omega 0 0, the Killing vector which has t plus omega phi combination. That time-like Killing vector becomes null on the horizon, and for the Kerr outer horizon you can define the surface gravity like this. Now remember, this theorem only is proven by using Einstein's equation. So this is a crucial open problem. Any extensions to general relativity, you have to assume that Killing horizon and event horizons are same. But this assumption may or may not be correct. This is a technical point, sometimes is missed while deriving the laws of thermodynamics beyond general relativity, that we do not have any proof of rigidity theorem, 4th dimension and higher dimension, without the use of Einstein's equation. They are only valid in general relativity. So it could be still possible to have event horizon in stationary black holes of some other theory which is not a Killing horizon. It will be interesting, but it is possible. Well, what is the use of this strong rigidity theorem? The use is that for event horizon, I really cannot define what is the surface gravity. But strong rigidity theorem guarantee my event horizon for stationary black holes is also a Killing horizon. So I have a notion of surface gravity attached to the event horizon using the strong rigidity theorem. Let me repeat, surface gravities are the properties of the Killing horizon. There is no relationship between Killing horizon and event horizon. Rigidity theorem ensures that in stationary spacetime, every Killing horizon and the event horizon is also a Killing horizon. In that case, I can associate the notion of surface gravity to the event horizon. Okay? And therefore, I can meaningfully talk about zeroth law for event horizon, not for Killing horizon, because event horizons are more interesting to me. They are causal boundary. Okay? Good. Then there is another concept which will be required. This concept is called the bifurcation surface. So if you remember the Schwarzschild extension of the Schwarzschild geometry, the maximal analytic extension of Schwarzschild geometry leads to these Kruskal regions, and this Kruskal coordinates, there exists the time-like Killing field in the full Kruskal coordinate is written in this way, okay, which is basically the Schwarzschild Killing field. In Kruskal coordinate it is sub L del V. So there exists a codimension 2 surface, that means in 4 dimensions a 2-dimensional closed surface, which is given by the equation V equal to 0 and U equal to 0, on which this Killing field vanishes. So if you look at the full Kruskal extension, this is the surface. This point, this is again at r equal to 2m, but in time it is in your past. Okay, this is a full analytic extension, so I am talking about eternal black hole. It is not a really part of your originally collapsing spacetime, but you can always attach a fictitious point to your collapsing spacetime. So this is a surface far in your time at infinite. Yes.
In the past if I'm in the black hole.
What?
It's only in my past if I'm inside.
You are inside here.
If I'm outside the black hole, it's space-like separate.
Well, this surface, what I mean is that this is the surface which is a part of the past horizon and your horizon. If you have a collapsing geometry, you don't have your past horizon, because that is inside the collapsing geometry. In that case, it's not a part of the real spacetime, because it's on the past horizon also, bifurcation surface. If you have a collapsing geometry, your past horizon is inside that matter. Well, okay, so such kind of surfaces are called bifurcation surface, because this is the meeting point of the past horizon and the future horizon. The past and future horizons bifurcate from that surface. Now, this is a 2-sphere. Of course, in d dimension, it will be a d minus 2 sphere, where the past and future horizon meet. A Killing horizon, any Killing horizon like Schwarzschild geometry, if it has a bifurcation sphere, we call it a bifurcate Killing horizon. Many of the proofs of the black hole thermodynamics and mechanics will simplify a lot, you will see immediately, if I assume that I am working with a bifurcate Killing horizon. Of course, this is an assumption. There is no guarantee that always you will have such solutions. But there are strong theorems which says, because of Wald and his student and his collaborator, which says that it is maybe always possible to extend the geometry a little bit to add these surfaces to a physical black hole collapsing surface. And so you will see that once I have a bifurcate Killing horizon, my proofs will simplify quite a bit. So let's go. For example, the Wald derivation of the first law explicitly assume that I have a bifurcate Killing horizon.
Are you claiming then that means that you can prove for solutions that do not have a bifurcated Killing surface that the thing that you can prove for the bifurcate is
okay.
also true?
I'll come back to this.
Is that a full proof or is this an argument that you can extend space-time?
This is an argument. This is an argument. I mean, well, one can show that certain analytic conditions holds true on the metric and certain energy condition hold true. It is possible to add part of this or extend part of the spacetime in an analytic way such that this is a part of the physical collapsing spacetime. That's all.
So that means you can prove.
Well, you can think of it a proof, yeah. I mean, what do you mean by a proof? I mean, it's a mathematical argument, so it is a proof. I'll calling it a proof. I'll call it a proof, which is by Wald, so it has to be a proof by definition. Okay. Well, so let's look at how the bifurcation surface actually helps us. Okay. So the zeroth law of black hole mechanics says the surface gravity must be constant on a stationary event horizon. Let's understand what is it. So this proves this statement. We will require either one of this. Okay. either we will use Einstein's equation with dominant energy condition, or we will use some form of symmetry but no field equation. Okay. So the best will be that if we can prove it without any field equation, just a kinematical statement. We do not have such proof. So either we will use Einstein's equation and dominant energy condition, or I use some form of enhanced symmetry even over and above the stationarity condition. Let's go ahead and see. So first of all, some geometry. The event horizon is a codimension 1 surface. So it's basically a 3-dimensional surface in 4 dimensions. You can think of in 4 dimensions topology to be a closed surface cross R. That's the event horizon. And then you can think of K's to be the generators of the event horizon, which obeys a null geodesic equation, and this L's to be the another null vector which completes the basis. And these gammas are the cross sections, the space metric on the cross section of the event horizon. So this is d minus 2 metric, and this is 1 1. So you have a decomposition of d minus 2 plus 2 decomposition. It's slightly general than the 3 plus 1 decomposition, just adapted to the null surfaces. That's all. And you can choose this basis to be like this and this following normalization conditions. That's all. So your metric on the event horizon is decomposed into this part. This is a metric on this KL null plane, and this is the metric on this d minus 2 dimensional space-like slice of the event horizon. So if you are in Schwarzschild geometry, you can think of this as u and v on the event horizon, and this is like a theta and phi direction on the event horizon. That's all. Good. So what we want to prove is this two statement. We want to prove if you move along the event horizon, then the surface gravity does not change. That is one part. Second, we also want to prove if you move along the other d minus 2 directions on the event horizon, then also surface gravity does not change. Okay. It's a codimension 1 surface, d minus 1 dimensional surface. So you should have proof that surface gravity does not change in d minus 1 directions. So this is one direction and this is d minus 2 directions. Okay. So first equation turns out to be very easy to prove, because the killing vector is related, the outside killing vector is related to this null generators of the event horizon by a proportionality constant. This is basically geodesic equations in different parameterization. K turns out to be a geodesic equation in affine parameterization, therefore this has this form, and this is a geodesic equation with non-affine parameterization. This T is sometimes called the killing time. So the killing vector generates the horizon, but the geodesic equation corresponding to it is in non-affine parameterization, and therefore it is related to xi and k by this proportionality constant. And you can immediately see in this convention lambda equal to 0 is my bifurcation surface. So I have fixed the convention such a way it becomes lambda equal to 0. You can put it at any arbitrary lambda. The proof is independent of that. Once you do that, you can show the change of the surface gravity is given by this equation. Basically what you do is that you take this equation and you calculate the change of surface gravity by taking derivative in both sides. You have to be a little careful because this equation has only meaning along the horizon. So therefore the projections of the derivative must be clear. And then use the properties of the killing vector, you get this equation. Now you can clearly see if I now just contract this equation and another killing vector, then since this is antisymmetric, this is alpha and this is alpha, this part vanishes. I have not used any field equation. You can just the definition of the surface gravity ensures the surface gravity is constant along a generator. That means along the time direction, quote unquote time, it's an affine time direction, the surface gravity cannot change. Okay. So only possible change of the surface gravity can be across the theta phi direction in Schwarzschild geometry. Okay. Of course, in Schwarzschild this is by definition constant, but in general case, the only possibility that surface gravity can change is along these angular directions. Okay. And note that to prove that I have not used any field equation. This is just a kinematical fact on the horizon. Good. So this is what we have. Now one can also now show that this is true. So what one does is that you take now derivative along the direction of gamma, contract this R using gamma and metric and everything, you can ultimately find this equation. So this tells you how the surface gravity changes along the space-like direction. Now you see the beauty of the assumption of bifurcation surface. If there is a bifurcation surface, that on that surface xi is 0. So at least on that surface kappa does not change. Okay. So suppose this is the bifurcation surface, so on that surface kappa is constant, but it is ensured that kappa cannot change along this direction, light-like direction. Okay. So once the bifurcation surface exists, if it is constant along one surface, it will be constant everywhere because the same value of kappa will go up. Okay. So you take anywhere you take a cross section, it will be same. Okay. So the bifurcation surface, if it exists, this is 0 on one slice, and therefore by this condition it is constant at every slice. You do not require any field equation. So if the bifurcation surface exists, then the surface gravity cannot change along the generator, which will immediately establish that at every cross section surface gravity is constant. So if for bifurcate killing horizon, zeroth law is just a geometric fact independent of the field equation. Yeah.
It seems like a very complicated technical way to show that if you assume that geometry is constant in time, anything you define from the geometry will be constant in time.
So this fact is indeed that. This fact. This is just saying that, but this is more non-trivial. This fact. It does not assume any symmetry in theta phi direction. So this is, as I said, this is a trivial fact. This is just saying that kappa does not change because all these slices are connected by killing isometry. So of course they should not change. But that doesn't guarantee that along the theta phi direction, so the main problem is to prove this. The whole technology is there to prove that this is constant 0. There is no guarantee that this will be 0 unless you assume special cases. Let me tell you what happens if I use Einstein's equation. Now suppose you use Einstein's equation. So now what you do, instead of RAB you replace it by Einstein's equation. So this side will become the stress tensor. Okay. You do not want to use the assumption that the surface gravity does not, the bifurcation surface exists. Now this part, you want to prove this part is 0. How do you prove this part? First of all, you use then the dominant energy condition. Dominant energy condition basically says that this vector cannot be a space-like vector. It has to be either null or time-like vector. Next, you know that the stationarity implies that the flux to the event horizon is 0. Okay. So that means this vector contracted along xi is 0. It cannot be a non-space-like vector, so it cannot have any component across the horizon. Okay. So the only component it can have, if this has to be true, is along itself, because xi dot xi is 0. In that case, this term is identically 0. So as you see, if the field equation changes, we need to redo the derivation. This derivation is no longer true once you change from Einstein's equation, because this here you have to impose Einstein's equation to go to this fact. Okay. If you do not have Einstein's equation, you will have extra term, and you have to be careful in tackling those extra term. Okay. So there is no guarantee. So you see what I am doing. Either I am assuming special symmetry, special consideration to prove this is 0, or I am using Einstein's equation and energy condition. So if there are higher curvature corrections, we expect Einstein's equation to change. For example, there will be new terms proportional to some dimensional full constant. If you have higher curvature correction, whatever this h could be, like a contribution from r square, RAB or whatever. Okay, but you expect it to change. In that case, the zeroth law for stationary black holes in arbitrary higher curvature gravity, it's still an open problem. We do not know for proving for arbitrary case, can we prove it? There are proofs for Lovelock case, and you can look at this, our work, where we show that, and that proof itself is quite non-trivial, because highly non-trivial geometric properties has to be used to set it to 0. So this is the issue of the second law, the zeroth law. Zeroth law, we can prove it if I assume Einstein's equation and energy condition with full generality, only assuming stationarity. Otherwise, we have to assume either bifurcation surface exists, or sometimes you can assume simple thing. For example, if you assume that the space-time is static instead of stationary, then you can show that surface gravity is constant without using field equation. But that's too of a, in relativity literature, people will not like if you prove something only for static space-time. Ideally you want to prove it for general stationary space-time. Okay. So that's the status. So this is still an open problem, and it will be good to have certain understanding. So if you look at the world's derivation of the first law, he will always assume bifurcate killing horizon, so that he can take away the surface gravity inside of his integrals. Okay, the bifurcation surface is important. Yes?
There are no known counterexamples.
There is no known counterexample though, as far as I know. As far as I know. In fact, in this paper, we tried to look for construct counterexample, we failed. Okay, the first law. So after zeroth law, let's go back to first law. So for the derivation of the first law, of course, ideally one can always look at the world's way of deriving, but I'll give you a simplified version where basically the things are same, but the mathematics simplifies a lot. So therefore, I will construct a static asymptotically flat vacuum black hole solution. Okay, of course, I know that the No-Hat theorem says that the uniqueness theorem says that such solution is Schwarzschild secretly, but for the time being, let's just consider to be static asymptotically flat vacuum black hole, just for the, so that I have to write less mathematics here. Okay, you will see that since static I will not have a rotation term, so I'll remove that rotation term, but you can always add, those are just details. So such a spacetime will have a killing vector like this. So you can define, so this is the structure of such a spacetime, this is the time like infinity. You can define what is called a Koman mass, which is basically ADM mass for this spacetimes, which is given by this formula. And this mass formula is defined at the I naught. This is basically the boundary term of the Hamiltonian of general relativity evaluated at the space like infinity. Okay, good. Now you can immediately, what you do is that you can use Stokes theorem. You can think of this codimension 2 surface as a boundary of this codimension 1 surface. This has this boundary and one boundary on the horizon. Okay. Now you can immediately write down a Stokes theorem, which is this integral equal to this plus this. This minus sign, relative minus sign, is because the normals are in different direction. That's all, just a convention. Good. Then you can show that you can this Koman mass can be written into this form. This is an identity. So this part comes from this integration on this and using Einstein's equation, and this part is the integral on this. Okay. Now my assumption, since I assume vacuum, this part goes away. That's why I assume I don't have to worry about this term. Of course, for Reisner-Nordstrom black hole, you have to worry about this term. It gives you the correct terms. But for simplicity, let's throw away this term by assuming vacuum. So I have the Koman mass or the ADM mass is related to this quantity evaluated at the horizon. Now what you can do for a static spacetime, you can actually evaluate by using this object here, evaluate this quantity, and this quantity turns out to be this, where T and S are given by this formula. Don't be afraid, the H bar indeed cancels out. This is a classical formula. So this H bar is just introduced for a bookkeeping. Okay, there's nothing more than that. So this formula is basically the smart relation, okay, written in a little bit different way. And you can see it's a highly non-trivial relation. It relates something at spatial infinity with something at the horizon through this Stokes theorem. Good. And you should think of what happens in D equal to 2 case. Well, now what I do is that I have such a static black hole solution. This asymptotic masses I cannot change. So even if I do something inside, the ADM mass does not change. Okay. The physical process is not going to change the ADM mass. ADM mass is defined for everything. Whatever energy is and whatever processes I'll do, ADM mass is defined at infinity. Now if I want to change this ADM mass, I have to consider a process in the space of solutions. So I think of in my head two static asymptotically black hole solutions which are connected by slightly differing ADM mass. Okay. Again, this is a process which is happening in the space of solutions of general relativity. Okay. In the phase space of general relativity. So this D is a change in the phase space of general relativity. If you do that, you can immediately write down that this dm is some T ds plus S dt. You can use a general form of this metric, define the location of the horizon, surface gravity, and you can show this equation magically reduces to this form. Okay. But of course, I have defined S to be the Bekenstein entropy and T to be the Hawking temperature. So this is the poor man derivation of the first law, stationary, but this has given a name. We don't call it a first law, we call it a stationary comparison first law, because of the fact that this relates quantities evaluated at infinity and quantity evaluated at the horizon. It's a very global approach. That is because I cannot define a local energy density for gravity. Okay? So I have to talk about the entire space-time, mass of the entire space-time, and two solutions connected by slightly different masses. This is in essence what world does, but of course in a much more greater detail and much more generality. So this can be readily generalized, this simple derivation can easily generalized for a stationary black hole for any diffeomorphism invariant theory of gravity. What you have to have an appropriate notion of boundary quantities. Okay. Once you have that, you can use this machinery and to write down a general black hole. And then the first law takes this form where these terms come because I am considering a stationary black hole. So this is omega dj term, j is the angular momentum, is the angular velocity on the horizon with appropriately defined. And in general you can show that entropy is not proportional to area but a local function of the horizon geometry. So this Wald's theorem basically gives you a, a kind of a machine. Give me your Lagrangian, calculate this quantity, integrate this quantity on the space-like slice of the horizon. Whatever you get is guaranteed to satisfy this equation. Okay, that's like a magic. Okay. Again, there are important assumptions. I will come back to it while deriving this equation. And you can show that this quantity is basically the Noether charge of the Killing isometry which generates the horizon. Okay. So QAB is a is a second rank tensor, basically n-2 form, integrated of a n-2 surface. So it makes sense, and therefore it can show that this is nothing but the Noether potential of the Killing isometry that generates horizon. So there are strong assumptions. First and foremost assumption that the theory admits a stationary black hole solution with a regular bifurcation surface. What does it mean? Not only the bifurcation surface exists, but also limits of everything on the bifurcation surface is finite. This is a non-trivial assumption because if you can think of, suppose your theory has a vector field. Apart from metric, there is a vectorical degree of freedom, like Einstein ether theory. Okay. If you take Einstein ether theory, which has an extra vector field, if you take the vector field on the bifurcation surface, okay, and you want it to remain time-like, then it is suffering infinite boost. You can think of that each of these the Killing curves, integral curves are like having boost, and you are going close to the bifurcation surface, which is like a time-like orbit becoming null. You can think of this as an infinite boost. Any such extra vectorial degree of freedom will diverge. Therefore, if your theory have a fundamental vector field apart from the metric, you cannot do Wald derivation. So another case, if you want to define something like a first law, which I don't know what it will be, for extremal black holes, you have to be careful because extremal black holes don't have bifurcation surface. Of course, in that case the temperature will be 0. Okay. So these are the strong assumptions which is required, and on the bifurcation surface one can show that this n-2 form actually becomes equal to the horizon binormal. This is defined, this is a skew symmetric form which is defined using this object, and in that case the Wald entropy formula is given this. This minus sign is just convention so that I get A by 4 if I plug general relativity. So basically what it tells is that look at the horizon, construct this form, integrate this quantity on the bifurcation surface, and what you get is guaranteed to be the Wald entropy satisfying the stationary comparison version of the first law. Let me again emphasize this D here means change in the space of solutions. Okay. Good. Now Wald entropy has several ambiguities, but because this is a Noether charge construction, Noether charge construction definitely an ambiguity. You can always add, for example, another conserved potential to a Noether charge. Okay, it will not see any change. Now you have to guarantee that such ambiguities do not appear in the entropy expression and also in the first law. Otherwise, what are you calculating? So this is guaranteed by this paper, which Kang is one of the relatively old paper. Okay, it's a very interesting paper, and they have shown that if you do things carefully, as long as you have a regular bifurcation surface, that's again important. This bifurcation surface will come back as a recurring theme. Okay, it is guaranteed that none of these ambiguities will, although the QAV is not uniquely determined, this entropy is uniquely determined and first law is independent. Okay, this is guaranteed. And this stationary comparison law is free from these ambiguities. And now as an example, suppose you take an Einstein-Gauss-Bonnet gravity in d dimension, go back and put it into this formula. You can have two expressions. Direct calculation will give you this. Since it is stationary black hole, you can show this is exactly equal to this. What is this object? This is the d-2 cross section. So the horizon cross sections are d-2 spheres. That has an intrinsic curvature. So in Schwarzschild case, it is 1 by r square. Okay. So the intrinsic curvature is d-2 r. This alpha is the Gauss-Bonnet constant. And you can clearly see if you put alpha equal to 0, you go back to area. Okay. By the way, this is just the Wald formula. this is only true for stationary black hole. This equality is true always. This equality is true is only for stationary black holes. Okay. So this is the case for first law. But we will focus to a little bit simpler version of the first law, which basically this is started with also Wald and Ted and Parantini, and we call it the physical process version. Okay, this is I mean from physical point of view is more easier to look at. If you recall ordinary thermodynamics, look, in ordinary thermodynamics, if I give you two equilibrium state and I give you a non-equilibrium process in between, okay, and if I ask you calculate the entropy change, since it is guaranteed that entropy is a state function, you can choose an equilibrium path instead of an actual non-equilibrium path. You will get the same change, right? It is guaranteed. But I am in general relativity, I am working with matrix and curvatures and areas. There is no guarantee that entropy is a state function. I am just calling it entropy because Hawking has told me and Bekenstein has told me to calculate. There is really no statistical mechanical picture. So one has the world calculation, you can think of an equilibrium state version where you go from one equilibrium state to another equilibrium state through various equilibrium path. But physical process version is basically direct integration. I give you area of a black hole, you put certain matter into it, maybe a spherical thing collapsing into it, directly calculate the change of the area by integrating the geodesic equation and the Raychaudhuri equation, okay? And see whether it obeys certain kind of first law. So this is what is called the physical process version. The fact that world version, the stationary comparison law, and the physical process version gives you the same entropy is highly non-trivial. And it tells you that black hole entropy indeed behaves like a state function. Okay, at least in the classical GR computation. Good. So let's go ahead and talk about physical process law. The physical process law aims to answer this question. What is the time now?
20 minutes.
Another 20 minutes. Okay, so I'll go. What does this try to answer? It try to answer how the entropy and area of the horizon changes when a black hole is perturbed. Okay. So I have a black hole, I perturb it, and I want to calculate how the area is changing. How do you do that? Okay, first you define these two quantities. One is called expansion, other is called shear. For null geodesics, again, I will use a particular parameterization, which is called the affine parameterization, which is easier to do this calculation, but you can always choose a different parameterization, doesn't matter. So these k's are assumed to obey null geodesic equation with affine parameterization, that is Ka del A Kb is equal to 0. It's just, 0 is easier, okay. So what does this theta represent? It tells you the change in area per unit area, okay. So you have a small bundle of null geodesic, infinitesimal area, and you can define the change in this infinitesimal area per unit area. So it's a local function at the horizon. Note that if I have a stationary black hole, then theta is 0. I mean, think of a Schwarzschild. The Schwarzschild, of course, every cross section is the same area, 4 pi r square, right? So 4 pi into 2m square, so it does not change. Similarly, I can define what is called a shear. What is a shear? That these cross sections, the shape can change, okay? So such anisotropic change in the shape, I will call it a shear. So this is like it's a symmetric traceless part, okay, of a full tensor. There is no rotation, and all. That is because we'll always, for null geodesic, we'll be always able to, write down this thing as a hypersurface orthogonal system, and therefore the rotation tensor will vanish. So we'll only have a shear and a expansion. Given this, there is this Raychaudhuri equation which describes the evolution of the expansion of the null event horizon. So Raychaudhuri equation tells you that how this shear is changing if you move along the event horizon. Okay? And this is a completely geometric equation. It has nothing to do with general relativity, it's just a kinematical equation. It tells you this is the equation. Note that this is a second derivative equation in area. That's important. It's not a first derivative equation in area. It's a second derivative equation because this itself contains the derivative of the area. Okay. So from this, suppose you want to take. So what do you want? You want to get an equation for the change of area. So you have to integrate this equation. That's the idea, right? If you integrate this equation, you have to put certain boundary condition. Okay. Yeah. Those boundary conditions are important. In fact, we will see in the later part of the talk, those boundary conditions are related to the existence of the bifurcation surface in the past, and the future, those boundary conditions are related to the stability of the black holes. So you have to assume this perturbation of the black hole don't destroy the black hole. If you want to do it more rigorously, you can show that the future boundary conditions are related to the assumption of cosmic censorship. Okay, but we may not go to that extent. Okay. So what should I do? My model is this. I will assume that the black hole entropy is given by this formula. Okay. What does it mean? So this is one is understandable. This is the 1/4 of the area. But as Wald has taught us that if I go beyond general relativity, there could be corrections. Taking his lesson seriously, we will add some term rho. What is this rho? It's a local function of the horizon geometry. Note that it need not even be intrinsic function. It could be an extrinsic function, okay? It could depends on derivative of the normals of the horizon. For example, if you go back, for this case, the Gauss-Bonnet case is a very special case when I can write this is rho. I can write it as entirely as an intrinsic quantity. This is a d-2 quantity. So that means it's a function of the d-2 metric entirely. Okay, that's what I mean by intrinsic quantity. But for a general theory, for example, if you switch off everything and keep only RABCT term, there is no guarantee that you will get an intrinsic quantity. You may have derivatives of the normals evaluated on the horizon. Okay, so that is definitely not. Basically what I mean is that the extrinsic curvatures of the horizon will come into play, not only the intrinsic curvatures. Okay, where am I? Yeah, so this rho will have, could have intrinsic curvatures in it, but it has to be a local function of the horizon geometry. It must be, we will be able to construct things, the data given on the horizon. And I will construct the field equation to be like this. I will not assume any particular form of HAV till the end. I will try to see as far as I can continue with this. Okay, let's see what are the conditions required to this. And the idea will be, can I calculate the change of this entropy because of the flux by using Raychaudhuri equation and whatever, okay, by using this equation, field equation, by perturbing the horizon. And always remember the GR limit. The GR limit is rho equal to 0 and alpha equal to 0. So rho and alpha goes to 0, I will have general relativity. Okay, so this is my construction. So the model is that I have a black hole solution of this theory, whatever this theory is. Okay, I am assuming these are all generally covariant term. I am not assuming any violation of general covariance. I have a theory, stationary black hole, I will not assume any symmetry. It is being perturbed by extra stress tensor over and above this. Okay, there is some delta TAB. Okay, and I want to calculate the change of the horizon area order by order in the perturbation. A simple example will be, you have a short shell black hole. There is a, you can think of a shell coming into the short shell black hole of mass m, and short shell black hole is of capital M. So you want to calculate things in the ratio small m by capital M. That's your order by order calculation. Good. How do you change the entropy? The change of entropy is basically you take a derivative of this quantity, time derivative of this quantity. Okay. If you change time derivative of area, you will get the expansion, but since there is a rho, there will be new terms, and that's all. Okay. Again, you can clearly see if you put rho equal to 0, you go back to 1/4 of the theta, and that gives you the area change. Okay. Remember the definition of theta. Theta is changing area per unit area. So instead of theta, I will have this quantity, and I will define this quantity as some capital theta. So this is some kind of analog of geometric theta to some, we call it generalized expansion. That's whatever. Now what I do, this is the general, like this is one line calculation. What you do is that now you want to calculate the entropy, and you do a trick. What you do, you integrate by parts and you get this equation. Okay. So you get a boundary term evaluated at lambda 1 and lambda 2, two slices, and you get a integral. Okay. So just to give you this picture, so this is the bifurcation surface, this is some future slice, this is the flux of the energy density. If there is no flux of the energy density, event horizon would have been like this. So you can think of this length as an area, just a comic cartoon interpretation. So if there is no flux, this would have been the event horizon, area would have remained same. Okay. Since there is a flux, the area is changing. Okay. I want to calculate what is the change of area between a slice at lambda 1 and slice at lambda 2. And this is the general expression. The general expression contains a total derivative term and a total integral. Okay. Again, we should always go back and check the GR limit. We will do that. Now with this expressions, I will assume certain important crucial things. What are the assumptions I will do? I will assume there exists a bifurcation surface in the past. Okay. So even in the physical process law, I will assume that I can always extend the space-time and add a little bit piece which contains a bifurcation surface. Remember, my bifurcation surface in this construction is at lambda equal to 0. That means I fix my lower limit of that integral at lambda equal to 0. Past bifurcation surface, yeah. Okay. So if I fix the lower limit of integral at lambda equal to 0, this lower limit vanishes. Okay. Well, you can put it at lambda equal to lambda naught. In that case, you will have lambda minus lambda naught. That's all. It will always vanish. What about the upper limit? Now you assume certain important things. See, the upper limit could be at as high as lambda goes to infinity. Okay. You can have to integrate at a very high value of lambda. What you assume that this generalized expansion, which is basically expansion in area and the change in entropy. Okay. All these objects die down at infinity. So infinity in time, the asymptotic future. What you assume that this capital theta has died down more than the rate 1 by lambda. So this is your stability condition. You explicitly assume that your generalized expansion vanishes at infinity in time. So you part of the black hole, whatever the Lie derivatives, what are the changes in time, all changes die down at infinity. So after some time you can have a cross section in time where there is no change. Okay, things have stabilized. Okay, and therefore you evaluate, you put your cross section to, this is in the future stationary slice, so you call it lambda f. So what you are basically doing, calculating the entire entropy change between the past bifurcation surface and the future stationary slice. This is definition of the physical process law. So sometimes this is called the integrated version of the physical process law. So therefore in that case, this goes to 0 and it goes to 0 very fast compared to this lambda, as lambda goes to some very large value of lambda f. Okay. In that case, both the upper limit and lower limit vanishes. Okay. So I can ignore this total boundary term. So the entropy change is given by only this formula. Now you should immediately ask that what happens if I want to calculate entropy change between two finite slices? What is the interpretation of this boundary term? Well, I will not talk about it in detail. You should look at our paper, which is in 2007. These are with my students, collaborator Sumanto and my postdoc Avirup, student Akash, and we have shown there is a very interesting interpretation of this term can be given. This term can be shown to be equal to the change of the kind of a Brownioff-Tress tensor on the horizon. So see, there is a Tress tensor at infinity in holography. It's called the Brownioff-Tress tensor, which is equivalent to the membrane Tress tensor on the horizon. In the classic work, there is this membrane paradigm. You can have this membrane Tress tensor on the horizon. You can show there is an interpretation of this term as the 0, component of the membrane Tress tensor. I can discuss it later, but yeah. Tress tensor, membrane Tress tensor, yeah. TRESS stress, under stress, which is basically actually KAB minus KHAB evaluated on the horizon with extrinsic curvature. So there is a very nice interpretation one can give of this term. But I'll stick to the standard case, where you integrate from 0 to infinity. And in that case, there is no term and you get this term. Okay, this is the change, okay, where capital theta is given by this formula. Again, no use of any particular Einstein's equation. So this will be my last slide before I stop. Then you go back, what you do, you use field equation. How do you use field equation? So what you do, you again do it by part. Okay, no, okay, you don't use by part. What you do, you take d dt on this. So you have d theta d lambda rho d theta d lambda and the second derivative of this object. Whenever you have d theta d lambda, use Raychaudhuri equation. Okay, there's a long derivation, and in the Raychaudhuri equation, replace every RAB, basically GAB, with TAB minus HAB, which you can always do. You do not assume any form of the field equation, but you can. In that case, you get this beautiful but little bit suggestive form of the entropy change. Let's think of what happens in the area case, GR case. In GR case, this entire term is 0 because rho is 0. Rho is 0. A alpha is 0. So there is no such term in general relativity. You have this term and only this term. Okay. But once any derivation of GR is there, there exists this particular term. Okay, and this is highly interesting term which we need to bother about. But ideally you don't want this term, but we'll see what does the interpretation of this term. So I'll stop here. So far, so I emphasize that I have not assumed anything other than existence of a past bifurcation surface and future stability. And this is the general form of the change of entropy for any theory for which you can write down entropy density and you can use a generally covariant field equation. And then the next talk I'll show how to massage this equation and arrive, what are the next step of arriving the physical process law for this theory. Thank you. I think I'm right on time. Yeah.
Actually, I left 10 minutes for questions.
Okay, very good.
So you could have 10 more minutes.
Okay, and
Let's ask the question first, and
we can have it.
question, then we can.
I don't mind more time for the coffee.
Okay. Any question for this lecture? Eugene?
Yeah.
For this physical process law that you have, so for the event horizon, it's possible that the entropy is changing without any flux at all, right?
In that case, I mean, what you mean by T, there is no matter TAB, but there may be a gravitational wave going into it.
Nothing at all. The TAB
Okay.
can be entirely it can be zero, it can be spherically symmetric, and there is
Okay.
nothing fluxing across the horizon.
Okay,
The
but
horizon
there,
is growing.
but there has there has to be flux somewhere. It cannot be eternally zero everywhere.
Yes.
So if there is a flux, let's say I have a delta function shell. Okay, in that case, it goes into event horizon at t equal to t naught, but event horizon will start expanding from the behind. This has been taken care of here because since I am using affine parameterization, you don't see it. If you use non-affine parameterization, there will be an advanced green function multiplied with all this expression, which will ensure that such teleological behavior of the event horizon is properly taken care of. So this is, if you think of a shell which has this teleological behavior, so what you do, you solve the Raychaudhuri equation by using a green function which is advanced instead of the retarded green function, because you want to give the future boundary condition. So that can easily be incorporated into this function.
So you need this future stations.
Absolutely. Without that, cannot be derived. I mean, not only this, the area theorem cannot.
That does not exist in the real universe, right?
What?
That is the thing that does not exist in the real universe. Like the real universe, the black holes eventually just
Okay.
radiate away.
Good, very good question. But this is within the classical general relativity. Once you incorporate the Hawking radiation, the questions become extremely difficult. What you are basically asking, the end stage of black hole evaporation. Then it's a question which is related to the unitarity of the entire theory. Whether the entire theory is related to, that's a different level of question. But within the classical general relativity, as long as the black holes are stable, this is a usual assumption, which is, I think, is quite reasonable. But you're absolutely right. If once you incorporate Hawking radiation, go beyond classical thing, the question becomes very tough because you are asking, because the black hole is then an unstable system, it's radiating away. The question is what is happening to the end stage. That is related to information loss paradox.
So there is an alternative proof of the process version of the first law due to Sean Hayward, right?
Yes,
The
yes.
trapping horizon.
Trapping horizon,
There,
yes.
The area of the black hole can only increase if there is a local flux across the horizon. The relation between them is very direct.
Yes, yes. For the this is basically the quasi-local and local dynamical horizon. Such proofs are very powerful. First of all, those prove the trapping horizon or the local horizons. The definition of local horizon has one advantage, that they avoid this teleological nature. But they also have sometimes disadvantages. For example, it is not clear whether they can, there are some cases it is difficult to generalize them to higher dimensions. There are proofs which only very 4-dimensional in nature, because they have to use the Gauss-Bonnet identity on the horizon. As far as I remember, that there is no direct generalization of this, but Astekar told me there is some recent extension of this. So in that case, this problem of event horizon can be avoided. This is definitely true. Dynamical horizon in that case is better, but I'm not discussing dynamical horizon in this case. But this technology can be generalized to dynamical horizon. People have done it. Yeah, go ahead.
Yes. Other question? Okay. Okay, next.
Could you comment on the entropy of the extreme of black hole?
Well, this Ashok has developed a formalism, Ashok Sen, where they have a limiting formalism. You start with a near extremal black hole and define the world formula for that. See, for GR there is not much of a problem. Well, we'll trust area by 4. The problem is, what is the entropy of extremal black hole beyond general relativity? That is the difficult question. In that case, there is a formalism people have developed, particularly due to Ashok, that there exists a limiting procedure starting from near extremal black hole to extremal black hole. And in that case, it seems the microscopic calculations and the formula result matches. Then you have to trust that formula, because there is a microscopic derivation of that formula. But I should mention there is a paper by Sean Carroll, Lisa Landell, and there's another person I forgot. They discusses the subtlety of this limit. This limit of going from non-extremal to extremal is extremely subtle when two horizons r plus and r minus coincides. And they give some extra interpretation of the extremal black hole entropy. So that paper actually clarifies what are the term goes to 0, what are the extra term, how this is related to area by 4. So you may look at that paper. But I mean, for completeness, let me mention there is also a school of thought, minority it may be, which still believes that extremal black holes have 0 entropy. That is because if you do in a calculation like a path integral by Euclidean quantum gravity, extremal black holes are somehow at infinite distance because of that throat. Okay, and if you calculate the Hawking Euclidean gravity calculation, it gives you 0 answer. So, well, there is group of people who still thinks that issue of extremal black hole entropy is the extremal black holes have 0 entropy. But in my opinion, since there exists microscopic derivation, at least for certain class of black holes, and this limiting procedure starting from near extremal to extremal matches with the microscopic formula, I will trust that formula, because microscopic derivation is more robust.
Okay, no, good.
I think there is also another notion of horizons, such as apparent horizons.
Yes.
Do you have some comments on the relation between various horizons?
Okay. So apparent horizon is a concept, again, as is saying, is more local than event horizon. It does not have any teleological property, but apparent horizon is a space-like surface, and it is always inside the event horizon. So I'm not sure that apparent horizon makes sense as a causal boundary, because it's a space-like, but there are formulations of laws of black hole mechanics on apparent horizon also. And I mean, you can write down a law. Well, I'm not very sure that since apparent horizon is not a causal boundary, what does microscopically it means to assigning an entropy to apparent horizon? I am not very sure, but indeed the derivation exists, and derivation is quite robust, quite rigorous. The problem is that we do not have any microscopic understanding of non-stationary black holes. See, the calculations which I was telling you, and even the Strobinger-Buffer calculation, all these black holes are static, spherically symmetric black holes with non-trivial charges. For such black holes, there is no distinction between what is the apparent horizon or what is a event horizon, and also this, what is the I mean, the different definitions of horizons all give you the same surface. The distinction comes when you perturb the horizon, right? I believe that ultimately it is the microscopic structure which will tell you what is the right surface to take. That's my take on it. By doing a classical formalism, you can always write for different surfaces, different laws. It is interesting, and it is interesting to check how far this can be generalized. But unless you have a microscopic picture, you will not be able to tell what is the role of these surfaces in the ultimate microscopic theory of black holes. I don't think classical, semi-classical analysis is going to give you much of a, beyond this, any bigger picture. But that's my personal take.
Okay, other question?
Yeah.
No?
Your chance.
So just in comment to this thing that you mentioned, so Stokes has his microscopic derivation of the black hole entropy for isolated horizons.
Yes.
Which are not causal horizons.
Not causal horizon.
They are the no limit of these dynamic horizons.
Absolutely.
And in that case, they are not causal horizons, but he has a microscopic.
Yes. Yes. He does claim.
Of
Yeah.
the entropy. So do you have a comment about? I mean, that is then showing you that you can have a microscopic derivation for a non-causal horizon.
I would prefer not to comment because I have not followed those derivation quite well. So as far as I know, that derivations do have certain issues, but I do not understand this derivation completely. If there exist microscopic derivations of such black holes, then indeed I agree, such surfaces must be taken seriously. I agree to that. But my knowledge of LQG derivations is not very, it was highly superficial, so it's not correct to comment.
In terms of your search for this generalized proof of the zeroth law, you mentioned to us that if there is a bifurcated killing surface, then you can prove it.
You can prove it without even using, in any case.
So if you find a generalized proof that holds for non-Einstein theory,
Okay,
or dimensions, or whatever you want, then that will be a proof that this rather nebulous thing you say about how you can extend the space-time to always include a bifurcated killing surface is true.
Absolutely.
But there is no proof that you can always generalize the space-time.
Absolutely. I strongly agree.
So those two things are basically the same thing.
So in GR, what happens is that everything falls into place. See, in GR, I can prove that, in the only stationary black hole solution, asymptotically flat vacuum solution is Kerr. Okay. I can prove, so Kerr has, not only that, I can also prove a zeroth law with only stationary black hole solution if I use Einstein theory. But at the same time, I also have theorems like uniqueness theorems guarantee that every stationary black hole is just Kerr. Okay, so everything becomes fitting with each other. Once I go beyond general relativity, I don't have those handles, so I have to prove it case by case. But if I have a general proof of like what you are saying, then of course that would be great. But that doesn't exist. Even generalizing the rigidity theorem for higher dimension, that itself is very recent.
This existence of the bifurcation surface, once the dynamic black hole for metric is given, does not depend on the theory. Once we have the metric.
Okay, I do not remember the proof. I do not exactly recall whether the Einstein's equations have been used. Rigidity theorem, if it is not used, then probably I have to look at the proof. I don't remember it at all.
It's just, I mean,
This world and a student is this Romanian student. I forgot. I have to look at the proof. It's a CQG paper. I remember the paper.
okay, we have many questions, so let us take this lecture again. We have 10 minutes break, so the second lecture starts at 50 and 50.
10 minutes. 15.
15?
Maybe 15 will be better.
Okay, our lecture allows 15 minutes for the break.
5 minutes concession.
Okay. So we meet starts at 10:55 for the second lecture.
됐죠?